Hello everybody. So what I'm going to go over today is how to find your minimum number of trays as well as your minimum reflux ratio for multi-component distillation using the Fenske and Underwood equations for multi-component distillation. So let's just pick, let's just pick 4 of these hydrocarbons from the deprecer chart that we want to try and separate. So let's just try initially to do octane. We'll try octane. Let's do isopentane. We'll do propane, and we'll do ethane. So we'll do C2, C3. We'll do CI5, and we'll do C8. So let's also just assume that we have a feed that's equal to 1,000 kilomoles per hour. We'll also assume that it is a saturated liquid. And let's give this some composition. So let's say this is 8%. Let's say this is 30%, 50%, and that leaves the rest of 12%. Okay, so let's do this problem here now. So let's assume again. Let's draw our distillation column first. So let's assume also that it's a total condenser and a partial reboiler. We have this feed that's coming in at 1,000. We have that it's a saturated liquid. We're going to have our bottoms, our distillate. Let's say that we want a 99% recovery of our propane and a 99.2% recovery of our isopentane from the bottom. So this will be in the distillate and this will be in the bottoms. So if we have a solution that's 8%, 30%, 50%, and 12% C2, C3, CI5, and C8, and we want a fractional recovery, so that's going to be our fractional recovery, and that's going to be a fractional recovery of 99% and 99.2% of our propane and our isopentane. So let's just say that our C2 is a non-light key, our C3 is our light key, our CI5 is our heavy key, and our C8 is our non-heavy key, or heavy non-key, I think is what it's supposed to be. Either way, it's not important. It's a non-key. So what we need to do first is, we need to also give this a pressure. So let's just assume, what's a nice one? Let's just say that the pressure is equal to 300 kPa. Okay, so I think we have enough information to go by here and to start initially using our, moving forward with the problem. So one thing to note is that since it is a saturated liquid or feed, so referring to just our feed right now, since it's a saturated liquid, our Z of our I is just equal to our X of our I. So there's no, it's not a two-phase, it's just a saturated liquid, so everything is a liquid component, so it's an X. Also from very early on in the class, we know that our summation of our Y components is equal to our summation of our K values from the deprecer chart times our Xi. So what we want to do now is this must be 1. Must be equal to 1. It can't be greater than or less than. So what we need to do then is we need to get K values from the deprecer chart and multiply them by our X component, or our Z component of our Z fraction of each component, and sum them up to make sure they equal to 1. If they don't equal to 1, we have to guess again and figure out a new temperature. So there's no temperature given, so we can't just connect to a temperature range. So we're going to have to use a bit of a guess and check method. This temperature that we're going to be finding, since it is a saturated liquid, this temperature that we're solving for is also going to be the boiling point of the solution that we have. So we are essentially using a guess and check depressor chart method to figure out what our boiling point is for this solution at this given pressure of 300 kilopascals. So let's try for an initial guess. And for an initial guess, what you can do is you can say that you want your light key K value to be greater than 1 while also keeping your K value for your heavy key less than 1. So what that looks like is you want your K C3 to be greater than 1 and you want your K CI5 to be less than 1. So let's come up here. We know that we're going to be starting at 300, so let's create a line there. We have our propane that we want to look at, that we want it to be greater than 1, but we also want our isopentane to be less than 1. So our isopentane less than 1 is here. This also gives us a value greater than 1 for our propane, so let's just stop it right there. I'm going to go a little bit lower so that I can get a nice value. That's good enough. So let's start reading off these K values then. For our first guess, this is going to be a temperature corresponding to, call that T1, is equal to about 66 degrees C. And for that, we have a K of KC2, we're going to have KC3, K8. So just reading these values from the depressor chart, our ethane is going to be approximately, you can say, 15.2. That's supposed to be 15, or I'm sorry, we can say 15.5. And for our propane, we're down here, I'm just going to say it's about 6, maybe 6.2. And then for our isopentane, oh, so I incorrectly did this because we want our isopentane to be lower than 1. So let's do this again. Okay, so this new temperature corresponds to approximately, let's say, 48 degrees. Now at this, our ethane value is 12.5. Our propane value is 4.6. Our isopentane value is approximately 0.7. And our octane value is, it gets real messy. I can say about 0.052. No, 0.032. Okay, so these are the values that we got from the depressor chart over here, our K values, using our initial temperature guess. So what we need to do is then plug these K values in for this, multiply them by the mole fraction that we have entering the feed that's in our feed composition, and we need to check to see if it's going to be equal to 1. So to do that, we just say 12.5 times 0.08 plus 4.6 times 0.3 plus 0.7 times 0.5 plus 0.032 times 0.12. And that's going to be equal to, the value we get for this is going to be 2.7, about 2.73, which does not equal 1. So we need to guess a new temperature. There is a somewhat of a optimization formula, I use that term loosely, that you can use to give you a new temperature guess, and we can say is your new guess temperature is just going to be equal to the K value of your reference, which in this case we chose our light key to be our reference, over our summation value that we had, so our KIXI. So what's going to be is it's going to be this for the time being, we're using our light key as our reference. So it's going to be 4.6 divided by 2.73, which gives you 1.68. So we can say about 1.7 degrees C is our new gas. So let's go up and create a new line. So from here, if we go from 0.3 to about 1.7, it's about there. And let's read these new values now and see what we get. I'm going to change the color. So for this, we have I believe we said it was ethane, propane, isopentane, and octane. So we have a K2, K3, K5, and a K8. So looking at our ethane, it's about, we can say about 6.1. For our propane, it's about 1.5, 1.7. For our isopentane, it's approximately, it's about 0.14. 0.14, and then for our octane, it looks like it's very, very small. I believe that is, let's see, this is 0.015, 0.004 it looks like, so we'll say 0.003. I believe is what that is. This looks like 0.002, so let's just say 0.003. Let's see what that does. Okay, so using the same formula, we're going to multiply these values by the composition. So this is equal to 6.1 times 0.08 plus 1.7 times 0.3 plus 0.14 times 0.5 plus 0.003 times 0.12. That's going to equal. So what we get here is that's going to equal to about 1.068. Is that close enough to 1? For the sake of this problem, we will say that it is. So we're going to say that these are our K values, and we're going to record that temperature, which was just the new temperature that we said right here. So we're going to say that the temperature, the boiling point of the temperature of the solution is going to be equal to 1.7 degrees C. So we have our K values, and so what we can do now is we can move forward with the problem to figure out what our minimum number of trays are. So to figure out the minimum number of trays, we need to use this equation. So we know that our N-min is equal to the fractional recovery of our light key times the fractional recovery of our heavy key over 1 minus fractional recovery of the light key is 1 minus the fractional recovery of the heavy key. This is the natural log. That is all divided by the natural log of our alpha of our light key with reference to our heavy key. So what we need to do now is we need to change our reference. So since right here this term says that our alpha is our light key with respect to our heavy key, we're going to say that our heavy key is now our reference. So that means that's going to be this K value of our KC5. So let's just figure out what the alpha is for all the components. So let's just say alpha C2 with respect to CI5 is just the K of C2 divided by our reference, our heavy key. So it's 6.1 divided by 0.14. Alpha C3 referenced to, with respect to our reference, is 1.7 divided by 0.14. Our alpha CI5 with respect to itself is just going to be 1. And then our alpha C8, our reference, is just going to be 0.003 divided by 0.14. Okay, so that's going to be our alphas of each component with respect to the reference temperature. So now what we can do is we can just easily plug into this equation and figure out our minimum number of trays. The hard part is over. So this is just going to be the fractional recovery of our light key. We said was, again, going back over here, 99. Times our 0.992. It's our heavy key. This is just 1 minus 0.99, 1 minus 0.992, natural log. All of that divided by the natural log of this value right here, our light key with respect to our heavy key, natural log of 12.14. So this will give us that our minimum number of trays is approximately equal to 3.77. So we'll say we need 4 trays is the minimum. Okay, so next step is to figure out what our minimum reflux ratio is. So in order to do that, we need to use a couple of equations. The first of which is going to be that the change in vapor from the feed entering, so the change in vapor flow rates as the feed enters the column is going to be equal to just the vapor flow rate. These are all just going to be given subscript m min because we're dealing with a minimum reflux ratio. So what this is this is the minimum vapor above the feed entering the column or the enriching section, and this is the minimum vapor, in the stripping section. So it's just vapor above the feed, vapor below the feed. It's going to be equal to summation of our components of alpha I with respect to the reference times our F times our ZI over alpha I ref minus this phi. I believe it's phi, minus this Greek term. Okay, but there is one thing to note. Since it is a saturated liquid, our change in V is going to be 0. So you can think of this as also going to be our vapor fraction times our feed. But since it's a saturated liquid, we don't have a vapor fraction. Our vapor fraction is 0. Therefore, this is going to be equal to 0. We're not having a change in vapor flow rate due to the feed being entered into the column. It's not, if it was a two-phase, this would not be true, but since it's a saturated liquid, it's changing. It would also be different if it was a subcooled liquid, because the subcooled liquid would have to cause a change in vapor flow rates because some of the vapor from the stripping section would condense out to heat up the subcooled feed, as we discussed in class. So this is all just going to be equal to 0. So 0 is going to be equal to alpha I R Okay, now our F can just go away. If we just divide by F, it doesn't change anything. Each one of these terms is going to have an F term in it, so it doesn't matter. So what we're essentially doing is we're just doing a summation of 4 terms, alpha I with our reference, times the feed composition of each one, minus our phi. So the whole point of this is to find our phi, and this is easy enough to do. We have all of these, so we'll just get that 0 equals. Okay, so this is what we end up getting. We only have 4 components in our feed, so we have 4 terms. Remember, these alpha values right here are just found from up here what we did earlier. All we're doing is we're taking our K value and dividing it by our K reference, which in this case our K reference was our heavy key. We use our heavy key as a reference just because of this portion of the equation for finding the minimum number of trays. You can use any reference you want. It's just easier to use this since this is what is required in the minimum number of trays equation. So from there, you just use algebra and you're able to figure out a value, numerical value for your phi. You can use a solver, you can work it out by hand. I'm not going to do that for the sake of this video. That's something that you can definitely do. But I will say the next thing, or the whole point of finding this phi, was to figure out what your V minimum is. So your minimum number of minimum vapor value that needs to be in the enriching section is equal to your summation of components, your IREF, times your distillate flow rate of each component times their fraction in the distillate. That's going to be divided by, so I'm going to just say in the distillate, minus this phi value. Okay, so it's the exact same thing above. You now have this phi value from before. You can plug that in, and you can figure out what your D is, and your the whole point of this is to figure out what your minimum vapor is. Now, to figure out what your D is and your I of the D, or your X of each component in the distillate, you need to just do mass balance. That's something that you should all be more than comfortable doing. You also need to make a couple of assumptions here. So one of the big assumptions is that if we have a fractional recovery of 99% of our light key, of our propane going up the top, that means we can just do 1 minus that to figure out what propane is going down the bottom. But the biggest thing is that we are assuming, since this is such a high percentage going to the top, we're assuming that anything above it, anything that's more volatile, is not going to be present in the bottom. So that's to say that our X of our C2 is going to be 0. We're not going to have any flow rate of ethane in our bottom composition. Similarly, we're going to say that our X component of our octane is going to be equal to 0 in our distillate. So since we have such a low percentage of our isopentane into the distillate, so we can figure out what our mole fraction of our isopentane is in the distillate, we could just take 1 minus. So if I were to just do an example, we have our feed flow rate of just our CI5 of our isopentane is equal to 1,000 times the 0.05, or I'm sorry, 0.5, because it's 50% of I5, CI5. So we know what our feed flow rate is of our isopentane, and we know what our fractional recovery in the bottom is. So if we want to figure out what is the bottom flow rate of our CI5, it's just equal to 1,000 times 0.5 times 0.992. That's what is flowing to the bottom of our CI5. That's going to be a very, very high percentage. We can also figure out what our distillate flow rate of our CI5 is. That's going to be our distillate flow rate of our CI5. It's just going to be equal to 1,000 times 0.5 times 1 minus this 0.992. It's a very small percentage. And so what we're saying is, since this is going to be a very small flow rate of our isopentane, we're going to assume that there's going to be no flow rate of our octane inside the distillate. Okay, so just to write that out, we are going to have a fraction of our C2, we are going to have a fraction of propane, and we are going to have a fraction of our isopentane in here. So this is easy. Anything that's flowing from the feed, this is just equal to the feed rate times the composition, times our Z of our CI5. Anything that's coming into the column is going to go up for ethane because it is more volatile than our light key. And then you can figure out what this is. This is just going to be our feed times our fractional recovery, whatever is coming in times the fractional recovery. And this we just did previously, and this is going to be equal to 0. So what you can do is you can sum those and figure out your distillate flow rate. Okay, that should be easy enough to do. If you have any more questions, please reach out to me. This Xi is going to be your component in the distillate. So you'll again have to do that using mass balance. Once you figure out what your Vmin is, it's pretty easy. You can just say Lmin is equal to your Vmin minus your distillate flow rate. We just figured that out previously using mass balance that you should be able to do at the very beginning of the problem using fractional recoveries and the assumptions that light non-keys are not in the bottoms and that non-heavy keys are not in the distillate. So that should be something that you should be able to do. And we just figured out our Vmin from before because you're able to find this value constant, plug it into this equation right here, get your Vmin, find your Lmin, and then your Lmin over D is a value that you should be able to get. I hope that helped. I hope that cleared things up. And if you have any more questions, please feel free to reach out to me or email me. Thanks for watching and have a great day.